So in this video, we're going to talk about second order differential equations as well as talk about the superposition principle. So you should leave this video understanding what those two things are. Okay, first of all, what is a second order differential equation? This is very simple for you to understand, simply because if you have an equation that can be written in this form, and g of x can be 0 or can be any number, we basically say that this is a second order ODE. Okay, remember that the power, basically the power being the number that you find over here, right? If the highest number that you find in an equation is equal to 2, the highest number that you find on any derivative of y is equal to 2, we basically say that's the second order ODE. So our goal is basically to solve second order ODEs with constant coefficients. So that's what we're going to be doing in this video and in the subsequent videos. So we're going to be solving second order ODEs with constant coefficients. But first up, I'm going to need you to understand a particular important principle that appears a lot in ODEs. Okay, what does this principle say? So simply put, if y1 is a solution to an ODE, so y might be equal to y1 might be equal to e to the power of x, or y1 might be equal to, let's do that, might be equal to cx plus b. I don't care what y1 is if it's a solution, and y2 is a solution. So y2 might be maybe b e to the power of x plus c or something like that. Let's just leave it. Or it can be maybe, I don't know, mx plus n or something like that. I don't care what y1 and y2 are, but if both of these are solutions to an ODE, then any linear combination is also a solution. So what do I mean by this? So it means that y is equals to c1 y1 plus c2 y2 also be a solution. So any linear combination will also be a solution. Now, we can prove why this is true, right? So basically try to derive why this is true. But as engineers, we don't have time for that. We're not doing math. So I'm going to do you better and expect you to appreciate this fact, and we're going to apply it, right? So I'm going to give you an example where we can prove that this fact is true. We're not going to derive where this fact comes from, but rather from a question, prove that any linear combination of solutions to a common ODE that we know can observe or obey this law. Okay, so that's how we're going to prove this. So an example that we're going to do, let's say y1, which is equal to e to the power of 3x, and y2, which is equal to e to the power of 4x are solutions. Okay, then our claim is basically any linear combinations of these solutions will also be a possible solution. So that's the superposition principle. Superposition implying the combined effect, so the combined effect of both of these will also be a solution. So that's what we mean by the superposition principle as applied to ODEs. So my claim is that if y1 and y2 are solutions, then superposing them, adding them together in a linear fashion should also be a solution. So c1 y1 plus c2 y2 is my claim personally. So that implies that y is equals to c1 e to the power of 3x plus c2 e to the power of 4x will be a possible solution. So I want to prove that this is true. So I just want to prove that it can obey this ODE over here. The first thing that I can try to find is basically find the value of dy over dx. You can easily integrate this and realize that that's going to be 3c1 e to the power of 3x plus 4c2 e to the power of 4x. You can also find the second derivative of this expression, which is thus the derivative of that derivative. So that's 9c1 e to the power of 3x plus 16c2 e to the power of 4x. So basically you can have two equations that are basically in this specific format that should satisfy this equation if this rule is true. Basically, if this is a solution, then this must satisfy that specific equation over there. So I'm going to just rewrite that equation. Okay, so I already know the value of the second derivative. Okay, so I know that it's 9c1 e to the power of 3x plus 16c2 e to the power of 4x. So I already know that this is true, so I can subtract 7. I already know that dy dx can be obtained as 3c1 e to the power of 3x plus 4c2 e to the power of 4x plus 12. I already know what c1 y is. Actually, it's c1 e to the power of 3x plus c2 e to the power of 4x. So this all must be equal to 0. And you can basically expand, right? So I have 9c1, right? So this is 3 times 7. So that's minus 21 c1. Then this is 12 c1 plus 12 c1, all of that e to the power of 3x. Then plus, we look at the other one, that's 16 c2 minus 28 c2 plus 12 c2. That's e to the power of 4x. That must be equal to 0. And you can proceed to find that 9 minus 21 plus 12, so 9 plus 12 minus 21, that's equal to 0. So all of this equates to 0. 16 plus 12, that's 28, minus 28, that's 0. So all of this equates to 0. So we have just proved that basically if one equation, which is e to the power of 3x, is a possible solution, e to the power of 4x, if it's also a possible solution, then a linear combination will be a general equation that can be true. So the general solution to this ODE. So if I were to tell you that for that ODE, y is equal to a, e to the power of 3x plus b, e to the power of 4x. If I were to tell you that this is the general equation, you can believe me, right? Because for any particular value of b, you can be able to satisfy this specific ODE for any particular value of a. So if you have specific values, so specific values of a and b will give you different solutions that can satisfy the same ODE. If b is equals to 0, you have just derived, and a is equals to 1, you've just derived y1, right? You can also derive y2, and there can also be other different families of solutions that can basically satisfy this ODE. But this is basically what we call superposition, right? If you have two specific solutions, you can superpose them together and linearly combine them. We're going to come back to this concept as we're going to be solving second order ODEs, right? So the next thing you must be asking me is, how did I know that this is true? Basically, how do I solve second order differential equations? So that's what we're going to do in the next video.